something is wrong with the universe. James Webb, a $10 billion telescope with eyes sharper than anything ever built, pointed itself at the edge of everything, and what it found shattered the rule book. Galaxies too massive to exist, stars older than they should be, objects no one has a name for, a black hole floating alone with no galaxy around it, and a signal suggesting our entire solar system is moving more than 3 times faster than science says it should. If you've ever wondered why scientists keep calling this a crisis, you're about to find out. We'll meet the galaxy that died before it should have been born, the glowing red dots that might be a completely new type of object, and the moment a Nobel Prize-winning astronomer used the word crisis in public. If this keeps you up at night, hit subscribe, because it should. Let's go. December 25th, 2021. A rocket lifted off from the coast of South America and carried the most expensive scientific instrument ever built straight into the dark. The James Webb Space Telescope cost $10 billion and took 30 years to design. Engineers folded its golden mirror the size of a tennis court like origami just to fit inside the rocket. Once in space, it unfolded itself piece by piece over 2 weeks. Every single step had to work perfectly. If one hinge failed, the whole mission was over. It worked. Webb parked itself 1 million miles from Earth, far enough that our planet's heat could not interfere with its sensors. Then it cooled down to nearly -450 degrees Fahrenheit, colder than the surface of Pluto, so it could detect the faintest possible light. Astronomers around the world had been waiting for this moment for decades. They had their predictions ready. They knew exactly what they expected to see. The standard model of cosmology, the rulebook for how the universe works, had been tested and refined for over 60 years. Satellites, ground-based telescopes, mathematical models, all of them agreed. The early universe would look chaotic, small, young, messy, blobs of gas and dust slowly pulling themselves together into galaxies over billions of years. When Webb finally sent back its first science images in July 2022, scientists stayed up through the night to look at them, and then the silence started. The images showed galaxies, bright ones, massive ones, fully formed ones, and they were sitting right where the universe was supposed to be, a chaotic, unfinished mess. These galaxies looked like they had been growing for billions of years, except the universe was only a few 100 million years old at that point. One astronomer compared it to digging at the foundation of a building and finding a fully furnished apartment down there. It made no sense. The problem was immediate, clear, and undeniable. A galaxy takes time to build. Gas has to collapse. Stars have to ignite. Stars have to explode, die, and seed the next generation of stars with heavier elements. That process has a speed limit. You cannot skip steps. You cannot rush physics. Except Webb was showing exactly that. Galaxies that had skipped steps. Galaxies that had broken the speed limit of cosmic evolution. Within weeks, the papers started coming. Astronomers ran their numbers again. They checked their instruments. They questioned their assumptions. The numbers kept coming back the same. Galaxies that should not exist, sitting there, glowing, massive, fully formed in the earliest era of the universe. One scientist described the feeling as exhilarating and terrifying at the same time. Exhilarating because this is what science lives for, a genuine mystery, a real crack in the rulebook. Terrifying because the rulebook had worked for 60 years without a flaw this big. Webb had been in the sky for less than a year. It had pointed itself at a tiny patch of space, a patch smaller than what you would cover with a grain of sand held at arm's length. And in that tiny patch, it had found enough evidence to shake cosmology to its core. Something in our understanding of the universe was wrong, and it was about to get much weirder. Before Webb broke it, the standard model of cosmology was one of the most successful scientific theories in human history. It has a name. Scientists call it lambda cold dark matter. Most just say the standard model. It describes everything: how the universe began, how it expanded, how matter clumped together, how stars formed, how galaxies grew. and for 6 decades, every observation matched its predictions almost perfectly. Here is the basic story the Standard Model tells. 13.8 billion years ago, everything that exists exploded out of an infinitely small, infinitely hot point. In the first fraction of a second, the universe expanded faster than light. Then it cooled. Protons and electrons snapped together into hydrogen atoms. The universe went dark. For hundreds of millions of years, nothing happened that you could see. This period is called the Cosmic Dark Ages. Then gravity took over. Hydrogen gas began to collapse in on itself in tiny pockets. Stars ignited. The darkness ended. And slowly, over billions of years, those first stars clustered into galaxies, which clustered into galaxy groups, which clustered into the massive structures we see today. That is the story. And the evidence for it was overwhelming. Scientists mapped the faint afterglow of the Big Bang, a glow still traveling across the universe today called the cosmic microwave background. It matched the model's predictions down to tiny fractions of a percent. Scientists measured how fast the universe expands in different directions. It matched. They calculated how much helium should have formed in the first few minutes after the Big Bang. It matched. They tracked how galaxies cluster into giant webs of filaments and voids. It matched. The model did have 2 mysteries baked into it. Dark matter, something invisible that provides the gravitational glue holding galaxies together, makes up roughly 27% of the universe. Nobody knows what it is. Dark energy, a force pushing the universe apart faster and faster, makes up roughly 68%. Nobody knows what that is either. But even with those unknowns, the model worked. Predictions held. Science moved forward. The Standard Model also made very specific predictions about what the early universe should look like. In the first billion years, galaxies should be small. They should be dim. They should be irregular, still forming, still building up mass. Bright, massive, fully grown galaxies should appear only after several billion years of cosmic history have passed. Those predictions felt solid. Every telescope before Webb had confirmed them. Hubble, the telescope Webb was built to replace, had looked deep into the early universe and seen exactly what the model predicted. Small, faint, irregular proto-galaxies. So, when Webb launched, scientists were not expecting surprises. They were expecting confirmation. They were expecting to fill in details, sharpen the edges, measure things more precisely. They got none of that. What they got instead was a direct contradiction of the model's most fundamental prediction about the early universe. Galaxies that were too big, too bright, and too chemically complex. Galaxies that could not have grown that fast under the rules the Standard Model set. The model that explained everything else, the model that matched every observation for 60 years, had met something it could not explain, and Webb had only started looking. The first batch of Webb images arrived in the summer of 2022. Scientists were expecting to see the very first faint smudges of ancient galaxies, barely visible, barely there. Instead, they got something that stopped conversations mid-sentence. Bright galaxies. Everywhere, not just a few outliers. Hundreds of them, scattered across the earliest era of the universe. Galaxies that looked fully formed. Galaxies glowing with the light of billions of stars. Galaxies that, by everything scientists understood, had no business being there. One team of researchers spotted 6 specific galaxies that became a turning point. A scientist named Mike Boylan-Colchin at the University of Texas ran the numbers on these 6 objects. Each one existed between 500 and 700 million years after the Big Bang. That sounds like a long time, but compared to the universe's full age of nearly 14 billion years, it is a tiny sliver. It is like saying a human being fully grew up, built a house, and raised a family before their first birthday. And these galaxies were massive. Each one contained more than 10 billion times the mass of our Sun in stars alone. Some estimates put a few of them even higher. Under the Standard Model, that mass was impossible to accumulate that quickly. The model set a ceiling on how fast matter could collapse and convert into stars. These 6 galaxies had broken through that ceiling by a significant margin. Boyle and Colchin published his analysis in a major scientific journal. His conclusion: these 6 galaxies, if confirmed, were in direct tension with the standard model of cosmology. In science, the word tension is careful language. It means this should worry you. Other scientists pushed back at first. Maybe the measurements were off. Maybe the distances were estimated wrong. Maybe some of these objects were not as old as they appeared. Webb kept looking. The 6 became dozens. The dozens became hundreds. And crucially, Webb's spectroscopy, a technique that spreads light into its component colors like a prism, revealing what elements are present and exactly how far away an object is confirmed the distances were real. These galaxies were as ancient as they appeared. Each confirmation added weight to the same conclusion. The early universe had grown up way too fast. Think about it like a time lapse of a city. The standard model says you should see empty land, then foundations, then walls, then buildings slowly rising over years. What Webb showed instead was empty land one frame, then a fully built skyscraper the next. The construction phase had been skipped or happened so fast it left almost no trace. Scientists began proposing explanations. Maybe stars in the early universe formed with incredible efficiency, converting almost all available gas into stars with almost no waste. Maybe the first stars were more massive than any stars alive today, burning faster and hotter. Maybe dark matter behaved differently in the early universe than the model predicted. All of these ideas had merit. None of them fully solved the problem. One team described the situation with unusual directness. There was, they wrote, a growing chasm between theory and observation in the early universe, and that chasm was not closing. It was widening with every new Webb observation. Webb had been scanning the sky for less than a year. There was more ancient light still waiting to be captured, more records still to be broken, and what it found next made all of those explanations feel small, because the impossible galaxies were just the beginning. To understand why these early galaxies were so shocking, you have to understand one thing: building a galaxy is slow. Stars are not born instantly. Gas has to cool. Then it has to collapse under its own gravity into a dense core. That core heats up until nuclear fusion ignites, until hydrogen atoms start crashing together hard enough to fuse into helium and release energy. That process alone can take millions of years for a single star. Then that star has to live, burn, and die. When it dies, especially if it is massive, it explodes as a supernova. That explosion scatters heavier elements like carbon, oxygen, and nitrogen into the surrounding gas. Those elements are the building blocks for the next generation of stars, which form with more complex chemistry than the first generation did. To build a galaxy like the Milky Way takes billions of years of this cycle. Birth, death, recycling, growth, layer by layer, generation by generation. Cosmologists had calculated the maximum rate at which gas could realistically convert into stars given the conditions of the early universe. It is a number called the stellar mass fraction, and under the standard model, no galaxy should have converted more than a small percentage of its available gas into stars in such a short time. The 6 galaxies Webb spotted in those first images had apparently converted close to 100%. 100%. Think about what that means. Every particle of gas available turned into stars, with almost nothing left over. Astronomers call this maximum possible efficiency. The standard model said it should be physically impossible to hit that ceiling, especially in the very early universe when conditions were less favorable for star formation than today. Yet that is what the data showed. It is like finding a campfire that burned every single piece of wood in a forest without leaving a single stick unburned. Fires do not work that way. Galaxies were not supposed to work that way either. The problem goes even deeper. To build a galaxy with 10 billion solar masses of stars in less than 700 million years, the star formation rate has to be extraordinarily high, far higher than what the standard model allows. It is not a small discrepancy. It is not an error of a few percent. It is a gap wide enough that some scientists began whispering about something no one wanted to say out loud. The model itself might be missing something fundamental. That possibility was uncomfortable, but the data kept pointing toward it. To be clear, and this matters, the standard model still explains enormous amounts of what we observe in the universe today. The large-scale structure of galaxy clusters, the composition of the early universe, the cosmic microwave background, all of that still lines up. The problem is specifically in how quickly galaxies assembled their mass in the first billion years. That one piece of the model appeared to be broken, and every new Webb observation was tightening the problem, adding more examples, pushing the discrepancy further beyond what any reasonable adjustment could fix. The speed limit of the universe was being broken over and over again, and the universe did not seem to care. Something stranger, though, was still waiting. When Mike Boylan-Kolchin published his analysis of those 6 galaxies, the scientific community held its breath. He had not just said the galaxies were surprising, he had done the math, hard math, the kind that leaves no room for hand-waving. And his conclusion, published in the journal Nature Astronomy, was this: if these 6 galaxies were as massive as they appeared, and if they existed as early in the universe as the data suggested, then the standard model of cosmology was in serious trouble. To get a sense of how serious, consider this comparison. Imagine you are baking a cake. The recipe says it takes 1 hour. You come back 40 seconds later, and the cake is already baked, frosted, and sitting on a plate. You would not say you need to tweak the recipe. You would question whether you understood cooking at all. That is roughly the scale of the problem these 6 galaxies presented. Each one, seen between 500 and 700 million years after the Big Bang, held more than 10 billion times the mass of our Sun in stars. Some estimates pushed 1 or 2 of them toward 100 billion solar masses, close to the mass of our entire Milky Way today, which took about 13 billion years to reach its current size. These galaxies had done in a fraction of the time what our own galaxy took almost the entire age of the universe to accomplish. Boylan-Kolchin calculated the probability. The chance that the standard model could produce even one galaxy this massive, this early, was extremely small. To produce 6 of them, clustered in a region of sky that Webb was barely beginning to examine, stretched that probability to the breaking point. Scientists pushed back with possibilities. Maybe the mass estimates were wrong. Webb was new. Maybe there were calibration issues. Maybe bright, active black holes at the centers of these galaxies were making them appear brighter than they actually were, which would mean the star count was inflated. These were reasonable objections. Science is supposed to work this way. Extraordinary claims demand extraordinary scrutiny. So teams around the world went back in. They tested the mass estimates with different methods. They used spectroscopy to confirm the distances independently. They ran simulations trying to produce galaxies like these within the standard model. The results came back consistent. The galaxies were real. The masses, while uncertain, were in the right range to cause serious problems. One paper described the situation as in tension with the standard cosmological model at a high level of statistical significance. In scientific language, that is about as close to alarm as researchers usually allow themselves in print. But here is the part that made it stranger still. After more observations in 2023 and 2024, some researchers began revising some of the most extreme mass estimates downward. A handful of those 6 galaxies turned out to be slightly less massive than initial readings suggested. This did not solve the problem. Dozens of others had been found in the meantime, and the overall picture, too many massive galaxies, too early, remained unchanged and grew stronger with every new Webb observation. The 6 had been the opening act. What came next was the record breaker. On a night in April 2025, astronomers pointed Webb at a tiny region of sky and found something that earned an unusual nickname, the mother of all early galaxies. Scientists call it MOME Z14. It holds the title of the most distant confirmed object humanity has ever observed. Its light traveled for more than 13 billion years to reach Webb's sensors. When that light left the galaxy, our sun did not exist. Earth did not exist. The Milky Way was barely an infant. The universe itself was only 280 million years old. 280 million years after the Big Bang, that is where MOME Z14 sits. To put that in perspective, if the universe's entire history were compressed into one calendar year, January 1st would be the Big Bang. MOME Z14 existed on roughly January 7th. We are currently living in mid-December of that year. That is how close to the very beginning this galaxy sits. The team behind the discovery was led by Rohan Naidu at the Massachusetts Institute of Technology. When he and his colleagues confirmed the distance using Webb spectrograph, an instrument that splits light into its component wavelengths to measure precise distances, Naidu released a statement that became famous in astronomy circles almost immediately. With Webb, we are able to see farther than humans ever have before, and it looks nothing like what we predicted, which is both challenging and exciting. That phrase, nothing like what we predicted, was not hyperbole. It was a scientific statement of fact. MOME Z14 is roughly 50 times smaller than our current Milky Way. So it is a small galaxy, at least in physical size, but it is shockingly bright. Brighter, more compact, and more chemically rich than any model predicted for something that formed so early. The brightness alone was a puzzle. Galaxies this young and this small should be dim, still gathering their first stars. MOME Z14 was blazing. The compactness was another puzzle. All that brightness packed into a space much smaller than expected. And then there was the chemistry. Spectroscopy revealed something that made astronomers stop and look at each other. The galaxy contained elevated levels of nitrogen, carbon too. These are elements that only appear after generations of massive stars have lived, burned through their fuel, and exploded. They are recycled elements, leftovers from stellar life cycles. A galaxy 280 million years old should not have enough generations of dead stars behind it to produce nitrogen at that level. The researchers noted the possibility that the early universe produced stars so enormous and so fast-burning that they could have cycled through multiple generations in an absurdly short window of time. Stars thousands of times more massive than the Sun, burning so hot they lived and died in a few million years instead of billions. MOME Z14 seemed to be a galaxy that had already lived several cosmic lifetimes before it should have had time to live one. And there was one more thing the data showed. MOME Z14 appeared to be clearing out the thick, primordial hydrogen fog surrounding it, blasting radiation into intergalactic space and carving a bubble of transparency in the dense haze of the early universe. This process is called reionization, and it is one of the key transitions in cosmic history. Webb was built partly to study when and how this clearing happened. Finding a galaxy doing it at 280 million years old pushed that timeline earlier than almost anyone expected. Whatever stars were burning inside this galaxy, they were extraordinary, burning hot enough to reshape the universe around them. And the chemistry those stars had left behind was about to tell an even stranger story. Nitrogen seems like a boring element. It makes up most of the air you breathe. You probably do not think about it much, but in cosmology, nitrogen is a timestamp. The early universe contained almost no nitrogen. When the Big Bang happened, the universe produced hydrogen, helium, and a tiny trace of lithium. That was the entire menu. Everything heavier, carbon, oxygen, nitrogen, iron, gold, had to be made inside stars through nuclear fusion and then released into space when those stars died. This process takes time. A massive star might live for only a few million years before exploding, but you need several generations of stars to build up significant amounts of nitrogen. The first generation of stars has to form, burn, and die. Their debris seeds the gas for a second generation of stars. Those burn and die, and so on. Each generation adds more nitrogen to the surrounding gas, which gets pulled into the next generation of stars. To get meaningful amounts of nitrogen in a galaxy, you need at least 2 or 3 full stellar life cycles, and each cycle takes millions of years at minimum. MOME Z14 existed when the universe was only 280 million years old. The stars in that galaxy were likely among the very first ever formed, and yet the spectroscopic readings showed nitrogen levels that implied generations of stellar death had already happened. The math did not work. At least, it did not work under any known theory of how stars normally form and evolve. The only way to get this much nitrogen this quickly is if the early universe produced stars so massive that they burned through their entire life cycle in just a few million years. We are talking about stars that could weigh thousands of times more than our Sunday stars, that are so hot they shine a million times brighter than the Sunday. Stars that live fast, burn out almost instantly on a cosmic scale, and explode with enough force to scatter heavy elements across enormous distances. No star like that exists in the universe today. The most massive stars we know of weigh around 100 to 200 times the mass of our Sun, and they are extremely rare. The stars implied by MOME Z14's nitrogen levels would have been 10 to 50 times more massive than that. Scientists have a term for these hypothetical giants. They are called population. 3 stars, the first generation of stars, formed from pure primordial hydrogen and helium before the universe had any heavier elements at all. Theorists predicted they might have been massive. Webb is beginning to suggest they were even more massive than predicted. And if that is true, the whole story of the early universe changes. Stars that massive do not just produce nitrogen, they generate enormous amounts of ultraviolet radiation that can tear hydrogen atoms apart across vast distances. They could have played a central role in ending the cosmic dark ages. They could have seeded the first supermassive black holes. They could be the hidden architects of everything that came after. MOME Z14 hinted at all of that inside its spectrum, but somewhere else in the early universe, another galaxy had an even stranger story, one that had nothing to do with being young and bright. This one was already old, already dead. Imagine a child in kindergarten who walks in already retired. Grey hair, pension, done with everything, never going to work again. That is roughly the situation astronomers found when they discovered a galaxy called Rubies, UDS QG Z7. In April 2025, a team led by astronomers from the University of Geneva announced they had found the most distant dead galaxy ever observed. This galaxy had stopped forming stars just 700 million years after the Big Bang. 700 million years. The universe was barely a toddler, and this galaxy had already lived its entire life. To understand why this is so shocking, you have to understand what a dead galaxy is. Galaxies grow by pulling in cold hydrogen gas from the space around them, which collapses under gravity into new stars. As long as the gas keeps flowing in, the galaxy keeps building new stars and growing. A galaxy dies. Astronomers call it quenching when it stops producing new stars. The gas runs out, or gets heated up, or gets pushed out somehow. In today's universe, dead galaxies are common, but they are old. They went through billions of years of furious star formation first, building up enormous masses before shutting down. That is the expected life story. A long, active youth, then a slow fade into stillness. Rubies, UDS, QG, Z7, had packed over 10 billion solar masses of stars into a space only 650 light-years across for reference. The distance from Earth to the nearest star is about 4 light-years and then completely shut down, all of that in less than 700 million years. The team searched through their models looking for a mechanism. In the early universe, galaxies are supposed to be growing rapidly. Gas is plentiful. The conditions favor star formation. Quenching was supposed to come later, after galaxies had grown massive enough for their central black holes to blow out the remaining gas with enormous jets of energy. We are not sure if any of those scenarios can explain what we have now seen with Webb, said co-author Roberto Maiolino from the University of Cambridge. That statement, from one of the world's leading galaxy formation experts, landed like a quiet alarm bell. The models built on decades of observations of the modern universe simply could not reproduce a galaxy that died this early. There was not enough time for the standard quenching mechanisms to operate. Something had reached in and switched this galaxy off before the rulebook said switching off was even possible. The team behind the discovery published their findings and acknowledged that models built on the modern universe would need to be revisited in light of what Webb was revealing. And Ruby's UDS, QG, Z7 was not alone. As Webb kept scanning, more quenched galaxies from impossibly early epochs kept appearing. Scientists dubbed them sleeping beauties, ancient, quiet, already done, in a universe that should still have been full of fire and formation. Each one was a mystery. Each one pointed toward the same unsettling conclusion. The early universe was doing things it had no business doing. Something strange was waiting just ahead, and it had a name no one was expecting. In the summer of 2022, just weeks after Webb began sending back its first science images, astronomers started noticing something odd. Tiny red specks. Everywhere. Every time Webb aimed its camera at a patch of ancient sky, these little red dots appeared scattered across the image. They were small, far smaller than a typical galaxy. They were compact, and they glowed with a distinctly reddish light. A handful appeared in almost every pointing of Webb's near-infrared camera. Astronomer Dale Kochevsky from Colby College in Maine was among the first to pay serious attention. He later described the moment as a trickle of papers that led to the realization that these things were really common. By 2023, hundreds had been catalogued. By 2025, the count was in the thousands. They appeared in significant numbers, starting roughly 650 million years after the Big Bang, and they were only present for a specific window of cosmic time. Around 2 billion years into the universe's history, they vanished from Webb's view, gone as inexplicably as they had appeared. This combination, extremely common, extremely compact, extremely bright, confined to one specific era, was unlike anything astronomers had ever catalogued. Scientists called them little red dots, and they had no idea what they were. The first instinct was that they might be very massive, very early galaxies. Galaxies so packed with stars that they appeared as a single bright point at such enormous distances. If that were true, they would be among the most massive objects of the early universe. But the math did not cooperate. If little red dots were purely galaxies full of stars, they would be the densest collections of stars in the known universe by a significant margin. One research team calculated that the most luminous ones were shining with the light of more than 250 billion suns, all squeezed into a space less than 1/3 of a light year across. By comparison, the distance from our sun to its nearest neighbor is about 4 light years. That density was physically implausible for a star cluster or a normal galaxy. So maybe they were not galaxies. Maybe they were the active cores of galaxies' supermassive black holes feeding on surrounding gas, which produces enormous amounts of light. That type of object is called a quasar. But quasars emit X-rays and radio waves in large quantities. Scientists looked for both from little red dots. Almost nothing came back. They did not fit the profile of a galaxy. They did not fit the profile of a known type of black hole. They were too bright, too compact, and too quiet at the wrong wavelengths. Whatever they were something the universe had made in enormous numbers during a specific window of time, and then apparently stopped making entirely. Scientists in early 2025 published a paper suggesting they might be something entirely new: black hole stars. Objects where a supermassive black hole sits at the center of a dense sphere of gas and provides all the energy, mimicking the atmosphere of a star but powered entirely by a black hole's feeding activity instead of nuclear fusion. The name sounds like science fiction. The data was saying otherwise, and the strangest single object Webb had found was still coming. In September 2025, a paper appeared in the journal Quanta that sent a ripple through the astronomy community. Scientists led by Roberto Maiolino at the University of Cambridge had found something that, according to the standard model of how the universe works, should be physically impossible. A black hole, floating alone, no galaxy around it, barely any stars, just a solitary monster in the ancient universe, shining with the light of an active feeding event, completely unattached to the structure that was supposed to have created it. They called it QSO-1. The object sits at a distance corresponding to 750 million years after the Big Bang. Its mass, approximately 50 million times the mass of our Sun. To be clear about the scale, if you replaced our Sun with this black hole, it would extend outward to a distance that engulfs every planet in our solar system and then some. And it was sitting out there, essentially alone. The standard model of galaxy formation had a clear story about how black holes and galaxies relate to each other. It went like this. First, gas collapses into the first stars. The most massive of those stars collapse at the end of their lives into stellar black holes. Those black holes merge and grow over billions of years into supermassive black holes. Galaxies form around them. The black hole ends up at the galaxy's center, where it slowly grows as the galaxy feeds it more gas. Black holes were supposed to come after galaxies, built from the wreckage of dead stars inside galaxies that had already formed around them. QSO-1 violated every step of that story. Maiolino and his team described it as a naked, supermassive black hole, a black hole that had somehow formed before its host galaxy existed in any meaningful way. 50 million solar masses, ancient, alone, and entirely unexplained. The team proposed two possible origins. The first, direct collapse. Instead of building up slowly from merging stellar mass black holes, this object may have formed when an enormous cloud of gas collapsed all at once into a single massive black hole, skipping the star formation stage entirely. The second, the black hole formed early, but then somehow consumed or expelled all the stars around it, leaving itself exposed. Neither explanation was particularly comfortable. Direct collapse required conditions in the early universe that are theoretically possible, but have never been confirmed. And a black hole capable of clearing out an entire galaxy's worth of stars at this early epoch raises questions about energy scales that push current physics to its limits. But QSO-1 was there. Observed, real, measured. The standard story said this object should not exist. Webb found it anyway. And QSO-1 was not the only one. In the months that followed, astronomers spotted additional early black holes that seemed to have formed before their surrounding galaxies had fully assembled. A pattern was taking shape. The early universe appeared to have been seeding black holes first, and letting galaxies build up around them afterward, completely flipping the textbook sequence. If that picture is correct, it means the supermassive black holes at the centers of galaxies, including our own Milky Way, may not be the product of stellar collapse and slow growth inside already formed galaxies. They may be ancient, primordial objects that formed under conditions the universe has not repeated since. And if a black hole could form before its galaxy, the entire relationship between black holes and galaxies in the early universe might be the reverse of what scientists assumed. Something in the universe was building itself in the wrong order, and it was not done yet. We had just found a black hole that formed before its galaxy. Now Webb was showing what black holes do to the galaxies that eventually grow up around them. The answer was not pretty. In 2023, a Cambridge team used Webb to study a galaxy nicknamed Pablo's Galaxy, sitting about 11.5 billion light-years away, meaning Webb saw it as it appeared roughly 2.5 billion years after the Big Bang. This galaxy had already stopped forming stars. It was massive, weighing around 200 billion times the mass of our Sun, but quiet, dead, done. Scientists suspected a connection between the galaxy's death and the supermassive black hole at its center, but they had never been able to confirm it before Webb. Webb confirmed it. The black hole at Pablo's galaxy's center was venting enormous quantities of gas outward, a process called a galactic wind. These winds were moving fast enough and carrying enough material to strip the galaxy of the cold gas it needed to form new stars. The black hole, in effect, was consuming its own galaxy from the inside. Every time it fed on surrounding material, it also pushed the fuel for future star formation outward beyond reach. Scientists called it a galaxy-killing wind. In 2026, a team published similar findings using Webb and a companion radio telescope. They found an early galaxy caught in the act, its black hole firing outflows powerful enough to drive gas out of the system entirely. No gas, no new stars. No new stars, a dead galaxy. These observations gave scientists a mechanism, something concrete, that could explain why so many galaxies in the early universe shut down so fast. A black hole grows, reaches a certain feeding rate, and begins blasting its own galaxy with enough energy to sterilize it. The scale of these outflows was staggering. Scientists estimated the gas being pushed out of some early galaxies at speeds exceeding 2 million miles per hour. At those speeds, the gas escapes the galaxy's gravity entirely and disperses into the surrounding intergalactic medium. Gone, unrecoverable, the galaxy is left with its existing stars, which slowly age, burn out, and fade, and no fuel to replace them. But the timing still did not fully add up. In the earliest dead galaxies, Webb had found like the one that shut down at 700 million years. The black holes would have had to grow massive and violent extraordinarily quickly, far faster than even the updated models could easily explain. And across all of this, the massive early galaxies, the dead early galaxies, the naked black hole, the galaxy-killing winds, a single pattern was emerging. The early universe was more violent, more efficient, and more complex than any model built before Webb predicted it could be. Something was accelerating everything. Some mechanism was pushing galaxies to form faster, grow bigger, and die sooner than the physics allowed. Each new Webb observation confirmed the pattern. Each one added a piece to a picture that looked less and less like the universe the standard model described. Scientists had competing theories, and one of them was stranger than any of the others. It involved the things Webb kept finding that no one had a name for. The red dots were back, and now they had company. In the same ancient sky, where little red dots glowed with their deep crimson light, Webb found something at the opposite end of the color scale. Bright blue galaxies, impossibly blue, blazing with intense ultraviolet energy, compact, dustless, and far too luminous for their apparent age. Scientists named them blue monsters. The name fits. In the early universe, roughly 800 million to 1 billion years after the Big Bang, blue monsters appear in Webb images as blazing points of electric blue, shining with more light than any model predicted for galaxies of their size and age. Normally, young galaxies produce plenty of dust. Stars form inside clouds of gas and dust, and the dying stars scatter more dust into the galaxy's surroundings. Dust absorbs ultraviolet light and re-emits it as infrared radiation. So a typical young galaxy glows red or orange in infrared images, the signature of all that hidden ultraviolet being absorbed and reprocessed. Blue monsters had almost no dust at all. That meant the ultraviolet light was escaping unobstructed, streaming out into intergalactic space with almost nothing to block it, which meant these galaxies were either forming stars in conditions where almost no dust could accumulate, or they were something else entirely. Some researchers proposed that blue monsters represented the most intense bursts of star formation in the history of the universe. Stars forming so fast, from gas so pure and primordial, that the usual dust never had time to build up. This explanation required star formation rates so extreme, thousands of solar masses of stars per year, that they pushed the very limits of what gas dynamics and gravity could produce. Others pointed out that blue monsters had another strange property. Their ultraviolet spectra showed a very specific shade of blue, not just bright, but unusually blue even for the most intensely star-forming galaxies known. And models trying to reproduce that specific shade of blue with bursting young stars kept falling slightly short. Then another research team pointed at a more radical possibility. The blue monster spectra, the chemical fingerprints in their light, looked remarkably similar to what theoretical models predicted for supermassive dark stars. Objects powered by dark matter annihilation rather than nuclear fusion, shining with an extraordinarily blue light and producing almost no dust because no normal stellar burning is occurring inside them. That idea sounds extreme, but it is a legitimate scientific proposal published in peer-reviewed journals, and combined with the little red dots, the naked black holes, the dead early galaxies, and the impossibly massive ones, it pointed towards something even larger than any single discovery. The early universe was hosting objects that did not fit into any existing category. Categories the Standard Model had treated as complete for 60 years. Something had been present at the beginning of everything that modern science had never predicted and barely understood. And it might have been the reason everything else grew so fast. Before getting there, though, the universe had one more massive problem to add to the pile. A problem that had been building quietly for almost a decade, a crack in the foundation of cosmology so wide that a Nobel Prize-winning physicist used the word crisis in public. The universe was expanding. Scientists could measure it from two completely different directions, and the two answers refused to match. That gap was growing, and Webb had just confirmed it was real. Before the crisis, something happened that showed just how deep Webb could see. In May 2026, astronomers released what they called the clearest map ever made of the cosmic web. The cosmic web is the largest structure in the universe. It is an enormous network of invisible dark matter filaments, long, thread-like strands that stretch for hundreds of millions of light years, connecting galaxy clusters the way power lines connect cities. Between the filaments lie vast empty voids, regions of space with almost nothing in them, billions of light years across. The filaments act as highways along which gas flows toward galaxy clusters, feeding star formation and galaxy growth. The Standard Model predicted this web would exist. Early simulations of the universe generated it from the initial tiny density fluctuations in the Big Bang's aftermath. Quantum-scale ripples so small they fit inside something trillions of times smaller than a grain of comfrey, sand, eventually stretching into the largest structures in existence. The web had been mapped before, but never with the clarity Webb provided. What Webb's map revealed was both confirmation and complication. The basic structure was there: the filaments, the nodes, the voids. The skeleton matched. But the details inside that skeleton revealed something unexpected. The web in the early universe was more tangled, more irregular, and more violently active than smooth simulations predicted. Galaxies along the filaments were forming and dying in patterns that did not match standard models of gas flow and galaxy growth. Some of the galaxies Webb found embedded in these early filaments were elongated, stretched out along the dark matter threads shaped not like round blobs or flat spiral disks, but like cosmic noodles, hundreds of thousands of light years long and just a small fraction of that wide. This shape was a serious puzzle. Standard cold dark matter models predict galaxies should grow roughly spherical or disc-shaped as they spin up and accumulate mass from all directions. Elongated, filamentary galaxies did not appear in cold dark matter simulations in large numbers, but they appeared constantly in Webb images of the early universe. A survey of more than 250 early galaxies found that most were chaotic, asymmetric, and elongated, nowhere near the neat disks or blobs the models produced. A team from the Massachusetts Institute of Technology, Harvard, and Taipei published a detailed analysis. Their conclusion: the elongated shapes were best explained by a different type of dark matter than the Standard Model assumes. They called it warm dark matter, or fuzzy dark matter particles that either move faster than the Standard Model's slow-moving cold particles or behave more like waves than point-like objects. If dark matter is warm or fuzzy rather than cold, the filaments of the cosmic web would be smoother, with fewer sharp clumps. Gas and stars flowing down those smoother filaments would naturally settle into elongated, stretched galaxies rather than round ones. Webb was finding exactly those elongated galaxies in large numbers in the exact epoch where the dark matter's nature would leave its clearest fingerprint. This was the clearest observational hint yet about what dark matter actually is, a question science has been trying to answer for over 80 years. The cosmic Webb map brought the picture into sharper focus, but the sharpness only made the flaws in the standard model more visible. And the biggest flaw of all was almost impossible to ignore. Here is the problem that has made cosmologists lose sleep for almost a decade. The universe is expanding. Every galaxy is moving away from every other galaxy as the space between them stretches. Edwin Hubble confirmed this in the 1920s. The rate of that expansion is described by a single number called the Hubble constant, and measuring that number precisely is one of the most important goals in all of modern cosmology, because it tells scientists the age of the universe, its size, and its ultimate fate. Scientists measure the Hubble constant in two completely independent ways, and the two ways give completely different answers. The first method looks at the early universe. Scientists study something called the cosmic microwave background, the faint glow of heat left over from the Big Bang, still traveling across space nearly 14 billion years later. Satellites can detect this glow in microwave frequencies. By measuring tiny temperature fluctuations in this ancient heat map, scientists can calculate how fast the universe was expanding when the glow was released, just 380,000 years after the Big Bang. Then they run the standard model forward in time to today and predict what the expansion rate should be now. That method gives a Hubble constant of roughly 67 kilometers per second per megaparsec. A megaparsec is about 3.3 million light years. The number means that for every 3.3 million light years of distance between two galaxies, those galaxies are moving apart at 67 kilometers per second, about 42,000 miles per hour. The second method works differently. Scientists build a chain of distance measurements that starts close to Earth and reaches outward into the modern universe. They measure the distances to pulsating stars, called Cepheid variables, whose brightness cycles let astronomers calculate how far away they are. Those distances are then used to calibrate exploding stars called Type Ia supernovae, which can be seen across billions of light years. By measuring how fast those distant supernovae are receding, scientists get a direct measurement of the expansion rate. Today, no model required. That method gives a Hubble constant of roughly 73 kilometers per second per megaparsec, 67 versus 73, a gap of 6 units. That sounds small. In cosmology, it is enormous. It represents a 10% difference in the measured expansion rate of the entire universe, depending on which end of cosmic history you measure from. The statistical confidence in this disagreement is at 5 sigma, a term meaning there is less than 1 chance in 3 million that this gap is random noise. In particle physics, 5 sigma is the bar for declaring a new discovery. This discrepancy has a name. Scientists call it the Hubble tension. For years, some astronomers hoped it was a measurement error. Maybe the Cepheid measurements used to build the local distance chain were slightly off. Maybe stars overlapping in dense fields were skewing the brightness readings. Hubble's camera could not always separate closely spaced stars. If the brightness of individual Cepheids was being contaminated by neighboring stars, the distance measurements would be off. And if the distances were off, the 73 number might be wrong, and the real answer might be closer to 67. The tension would evaporate. The only way to test this was with a sharper telescope, one that could resolve individual Cepheid stars in crowded fields without any blending. By 2021, that telescope existed, and what it found changed the conversation permanently. When James Webb launched, some scientists held out genuine hope that the Hubble tension would dissolve. The leading candidate for a clean fix was measurement error. Specifically, astronomers using the Hubble Space Telescope to measure Cepheid variable stars might have been getting contaminated readings. Cepheids in dense star fields can blur together with neighboring stars in Hubble's view, making their brightness harder to isolate precisely. If the Cepheid measurements were slightly off, the 73 number could be wrong and the real answer might be closer to 67. the tension would evaporate. Webb's sharper vision could resolve individual Cepheid stars in galaxies where Hubble had struggled. It could directly check whether the contamination hypothesis was real. Webb checked. The contamination was not there. Webb confirmed the Cepheid measurements with extraordinary precision, resolving stars individually in galaxies where Hubble had seen only blended smears of light. The brightness values Hubble had measured held up. The distance estimates built from those Cepheids held up. The Hubble constant from the local distance ladder came back at genuinely around 73. The gap between 67 and 73 was not a mistake. It was real. We've now spanned the whole range of what Hubble observed, and we can rule out a measurement error as the cause of the Hubble tension with very high confidence, said Adam Rees, the Nobel Prize-winning astronomer who had led the local distance ladder measurements for years. Combining Webb and Hubble gives us the best of both worlds. Nobel laureate David Gross had declared the Hubble tension a crisis at a physics conference in California back in 2019. By January 2025, at a major meeting of the American Astronomical Society, another leading astrophysicist made the same declaration from the podium. So here is the full weight of what that means. Two precise, independent, cross-checked methods of measuring how fast the universe expands give answers that differ by almost 10%. The method based on the early universe says 67. The method based on direct measurements in today's universe says 73. Both methods have been run by multiple independent teams. Both have been verified with multiple instruments. Neither method is obviously wrong. Something in the universe itself must be causing the discrepancy, and every reasonable mundane explanation has now been tested and ruled out. The only remaining options require new physics. Maybe the early universe contained a brief burst of energy called early dark energy that temporarily accelerated expansion before fading away, skewing the calculation based on the cosmic microwave background. Maybe dark matter in the early universe behaved differently than the cold, slow-moving particles the standard model assumes, altering the expansion history in subtle ways. Maybe there is a new particle or a new field not yet discovered, leaving its signature in the gap between the two measurements. None of these possibilities fit comfortably inside the existing model. All of them require either adding something entirely new or rewriting something foundational. Something was wrong with the rulebook, and what arrived next questioned the most fundamental force in the entire standard model, because dark energy itself had just been caught changing, and a constant that scientists had built 6 decades of cosmology on top of might not be constant at all. In 1998, 2 independent teams of astronomers discovered something that changed everything. The universe was not just expanding, it was expanding faster and faster over time. Something was pushing galaxies apart at an accelerating rate. Something invisible. Something that filled all of space evenly. Something that did not dilute as the universe grew, the way ordinary matter and radiation do. Scientists named it dark energy. Albert Einstein had actually introduced a similar concept decades earlier. He called it the cosmological constant, a term he later called his greatest mistake because he used it to try to keep the universe static in his equations. Before astronomers had confirmed it was expanding, he removed it from his equations. Now it was back. The standard model absorbed dark energy as a cosmological constant, a fixed number, an energy inherent to the fabric of space itself, the same everywhere and at all times, unchanging, eternal. That assumption, dark energy as a constant, became a cornerstone of the standard model. Then the dark energy spectroscopic instrument entered the picture. This is a telescope in Arizona built specifically to map the 3-dimensional distribution of galaxies across billions of years of cosmic history. By tracking how galaxies cluster and spread across time, it can measure whether the universe's acceleration has stayed steady or shifted. The instrument released its first major dataset in 2024. A second, larger dataset followed in 2025. The data told a different story from the constant. When the team analyzed galaxy distribution patterns across billions of years, the results did not perfectly match what a fixed, unchanging dark energy would produce. The pattern slightly favored a dark energy that was stronger in the past and had been weakening over time, evolving, changing, behaving like something with a history rather than a fixed property of space. The statistical confidence was high enough that multiple independent analyses confirmed the signal. The team published the results. Other groups dug into the same data from different angles. The signal persisted. A changing dark energy would rank among the biggest discoveries in science in the last 50 years. It would mean the cosmological constant is not actually constant. It would mean the force driving the universe apart is not a fixed property of space, but a dynamic field, something that can evolve, weaken, and potentially change direction. It would mean that Einstein's instinct was right in a deeper, stranger way than anyone assumed. Scientists proposed that this dynamic dark energy might be a new quantum field filling space, one with its own energy that slowly drains as the universe ages, like a battery gradually running down. If that is true, every cosmological calculation built on the assumption of a constant dark energy needs to be revised. The history of the universe's expansion, its predicted future, the age calculations, all of it sits on a pillar that might be cracked. The cracks were accumulating fast. 27% of the universe is made of something that emits no light, reflects no light, absorbs no light, and cannot be detected by any instrument ever built. Scientists call it dark matter. We know it exists because of how gravity works. Galaxies rotate at speeds that would tear them apart if visible matter were all they contained. Galaxy clusters bend light far more than their visible mass can account for. The cosmic web of filaments could not have formed from ordinary matter alone. Something massive and invisible is providing the gravitational skeleton on which the visible universe is built. But what that something is has been unknown for over 80 years. The standard model assumes dark matter consists of slow-moving, heavy particles that clump together in predictable ways. This assumption is called cold dark matter. Cold refers to the speed of the particles. Not a temperature cold dark matter particles move slowly compared to the speed of light. Cold dark matter makes specific predictions about galaxy shapes. In cold dark matter simulations, early galaxies tend to form in roughly round or blob-like configurations. The dark matter halos around them accumulate mass from all directions relatively evenly, and the galaxies that form inside those halos take on compact, roughly spherical or disc-like morphologies. Webb found something different. Across hundreds of early galaxies, a striking number of them were elongated, stretched, shaped like noodles or cigars rather than blobs or discs. A team that included researchers from the Massachusetts Institute of Technology and Harvard ran the observations against simulations of different dark matter types. Cold dark matter could not easily reproduce the abundance of elongated galaxies Webb was finding. But two alternative models could. The first is warm dark matter particles that move faster than cold dark matter particles. Faster moving particles smooth out the structure of dark matter filaments, making them more uniform and elongated. Gas and stars flow down those smoother filaments and form stretched, elongated galaxies naturally. The second is fuzzy dark matter, also called wave dark matter particles, so light that they behave like waves rather than individual particles. Fuzzy dark matter also produces smoother filaments than cold dark matter and also tends to generate elongated galaxies in simulations. Both alternatives produced galaxy morphologies in simulations that matched what Webb was seeing in the real universe far better than cold dark matter could. This did not prove that dark matter is warm or fuzzy, but it was the first observational hint based on the actual shapes of real galaxies in the real early universe that the cold dark matter assumption at the heart of the standard model might need revision. The shapes of those ancient galaxies were carrying a message, and the message was about the invisible substance that built the universe. But the most dramatic revelation about what was hiding in those early galaxies was still ahead, because Webb had spotted something in those same ancient images that no one had planned to find. something that required an entirely new category of object, something that might explain almost everything else at once. It lived in the dark, and it did not run on the fuel everything else in the universe uses. A star powered by nuclear fusion works like a furnace. Hydrogen atoms crash together under enormous pressure and heat until they fuse into helium. The energy released from that fusion pushes outward against gravity, keeping the star from collapsing on itself. That balance, gravity pulling in, fusion pushing out, is what makes a star a star. Every star in the night sky works this way. Every star scientists have ever measured. Every star in every galaxy across the observable universe. Nuclear fusion. No exceptions, except Webb may have just found one. In 2023, a team that included astrophysicist Catherine Fries at the University of Texas examined 3 unusual early objects in Webb's first images. These objects appeared at the very earliest epochs, some as far back as only 300 million years after the Big Bang. Their spectra, the fingerprints of light sorted by wavelength, did not match any known type of galaxy. They sat in a classification gap that had no name. Fries and her colleagues proposed one. These objects, they argued, might be supermassive dark stars. A dark star is a theoretical object first proposed in 2008. In the very early universe, regions of extremely dense dark matter could have trapped primordial hydrogen and helium gas. That gas would heat up through dark matter annihilation. When 2 dark matter particles collide, they destroy each other and release energy. That energy heats the surrounding gas. The gas expands. A massive, bloated, luminous sphere forms, powered entirely by dark matter destroying itself inside it. No nuclear fusion, no hydrogen burning, just dark matter annihilating and releasing heat. Dark stars would be unlike anything in the modern universe. Fries and her colleagues estimated some could grow to 1 million times the mass of our Sun, making them the most massive single objects ever to exist. They would be extraordinarily luminous, and because they run on dark matter annihilation rather than nuclear fusion, they would produce almost no dust and emit a characteristically blue spectrum matching precisely what Webb was seeing in the blue monster galaxies. In 2025, the team refined their analysis. One of the 3 candidate objects showed a distinctive helium absorption feature in its spectrum. Dark star models specifically predict this signature. Ordinary stellar populations do not produce it at the same intensity at those temperatures. The team described it as a potential smoking gun, not a confirmation, but a signal worth taking seriously. And the implications reached far beyond explaining a few strange early sources. If dark stars existed, they were likely the most massive objects the universe ever produced. When they eventually ran out of dark matter fuel, they would collapse not into ordinary stellar black holes, but into seeds of supermassive black holes, far more massive than any star could produce. Seeds heavy enough to explain why Webb kept finding enormous black holes in the very early universe, long before those black holes should have had time to grow. Dark stars might have been the engines that seeded every supermassive black hole in existence today, the invisible architects that made everything else possible. And Webb was finding their fingerprints in the most ancient light we have ever captured. The evidence was thin, but it was consistent, and it was growing. Dark stars were one proposed solution to the early universe puzzle. A second candidate emerged from an entirely different direction: chemical analysis. Webb's spectrographs, the instruments that spread incoming light into its component wavelengths, can detect the presence of specific elements in distant galaxies. By looking for the characteristic colors those elements absorb or emit, every element has a unique spectral fingerprint. Carbon absorbs light at one specific set of wavelengths, oxygen at another, nitrogen at another still. By reading those fingerprints in ancient galaxies, astronomers can reconstruct the chemical history of the stars that lived and died inside them. And in several early galaxies, the fingerprints were telling a story that current models could not reproduce. In November 2025, an international team published a detailed analysis of a galaxy known informally as GS3073, seen as it appeared roughly 1 billion years after the Big Bang. Its nitrogen levels were not just elevated, they were far beyond what any known stellar population could have produced in that timeframe. To generate that much nitrogen that quickly, the researchers calculated that stars of extraordinary mass must have been involved. Stars weighing between 1,000 and 10,000 times the mass of our Sunday. Objects so enormous they existed at the outer theoretical limit of what physics allows a category sometimes called population. 3 stars in their most extreme form, the very first generation born from pure primordial hydrogen and helium. Ordinary massive stars today, the giants weighing 50 or 100 times the mass of the Sun, are rare and short-lived, burning through their fuel in just a few million years before exploding. But stars at 1,000 solar masses and above burn so hot that they undergo a completely different kind of death. The explosion is called a pair instability supernova. The star does not leave behind a neutron star or a black hole. It tears itself entirely apart, scattering an enriched cloud of gas across enormous distances, carrying chemical fingerprints of that extreme burning event. GS3073's spectrum matched the theoretical predictions for pair instability supernova remnants with striking precision. The match was specific enough that the team concluded massive population, 3 stars, had almost certainly been involved in the galaxy's chemical history. This was not just a curious data point, it was a direct observation of the chemical legacy of stars that should not exist in any other epoch of the universe. Stars that massive cannot form today. The intense radiation fields produced by the many stars already shining across the modern universe break apart gas clouds before they can accumulate enough mass. Only in the pristine, radiation-free early universe, before the first stars had switched on, could such giants have assembled. Webb was finding their graves. Galaxies still carrying the signatures of stars that had burned and exploded billions of years before our own sun was born. The early universe had run on a completely different kind of stellar engine, and the exhaust from those engines was written in the chemistry of ancient light, waiting 13 billion years to be read. What made that realization especially striking was that it connected 2 separate mysteries Webb had uncovered. Any model of the early universe that did not account for stars of 1,000 solar masses was missing the dominant driver of chemical enrichment in the first billion years. And any model of early black holes that did not account for the collapse of those stars into ultramassive seeds was missing a major pathway to the enormous black holes Webb kept finding in the early universe. 2 mysteries, the nitrogen anomaly and the black hole mass problem, might share a single answer. Every model of the universe rests on one foundational assumption above all others. The universe, on the largest scales, looks the same in every direction. It has no preferred axis, no special orientation. Zoom out far enough, and matter is spread evenly across space. No lopsidedness, no cosmic up or down, no direction that is meaningfully different from any other. This assumption has a name. Scientists call it the cosmological principle. Without it, the mathematical equations that describe the history of the entire universe collapse. Lambda cold dark matter requires it. The predictions from the cosmic microwave background require it. The standard model of cosmology stands on it like a foundation. In late 2025, a study published in Physical Review Letters proposed that the cosmological principle might be wrong. A team led by astrophysicist Lukas Bohmer at Bielefeld University in Germany analyzed a large catalogue of radio galaxies, distant galaxies that emit powerful radio waves detectable across billions of light years. They measured how these galaxies were distributed across the sky, counting them in every direction, looking for any asymmetry in their spread. The standard model predicted a very specific, small asymmetry based on our solar system's known velocity relative to the cosmic microwave background. As our solar system moves through space, galaxies in the direction we are heading should appear slightly more numerous due to the Doppler effect, the same effect that makes a car horn sound higher as it approaches. What the team measured was 3.67 times larger than predicted. with a statistical confidence of 5.4 sigma, even higher than the Hubble tension. This is called the cosmic dipole anomaly. In plain language, depending on which direction you look, the universe appears structured differently. More galaxies appear clustered in one direction than the other, at a scale that cannot be accounted for by our solar system's known motion through space. Two explanations exist. Either our solar system is moving through the universe at more than 3 times the speed the standard model allows, pulled by some enormous invisible concentration of mass, billions of light years away, or the universe itself is genuinely lopsided in a way that the standard model explicitly forbids. Both options carry serious consequences. If an enormous mass concentration is pulling our local group of galaxies at that speed, it would need to be a structure far larger than anything the standard model can produce. If the universe is genuinely asymmetric at large scales, the cosmological principle is simply wrong. And if the cosmological principle is wrong, the equations that all of cosmology is written in need to be rebuilt from their foundation. This was not a marginal result. Subsequent studies using different radio galaxy catalogs and different analysis methods confirmed the signal. The anomaly persisted across datasets, telescopes, and teams. The universe was sending a clear message. Whether cosmology was ready to receive it was another question entirely. But there was something deeper in the Bohm result that scientists were still processing. Previous anomalies in the same direction, studies of distant quasars from the early 2010s, showing a similar asymmetry, had been published and largely set aside, awaiting confirmation with better data. The Bohm result was that confirmation, and it arrived at the same moment that Webb's impossible early galaxies, the evolving dark energy signal, and the Hubble tension were all demanding attention. For the first time, multiple independent lines of evidence were pointing toward the same conclusion. The universe was more complicated than the equations written for it, and somewhere in that complexity, a better description was waiting. In August 2025, astronomers at the University of Missouri published a paper that added 300 more mysteries to the pile. Using Webb's deep imaging data, they identified 300 unusually bright objects scattered across the early universe. Each one was compact. Each one blazed with light at a scale far beyond what standard models predicted for objects at their distance and epoch. And each one shared the same unusual brightness profile in near-infrared wavelengths, the signature of ultraviolet light that had been stretched by the expansion of space during its long journey to Webb's sensors. 300 is a meaningful number. A handful of anomalous objects can always be chalked up to measurement uncertainty, calibration quirks, or edge cases in a statistical distribution. 300 objects, all sharing the same unusual properties, all appearing in the same cosmic epoch, are a population. And populations demand explanations that go beyond coincidence. The researchers considered several possibilities. Some of the 300 might be intense, starburst galaxies, systems converting gas into stars at extraordinary rates, generating the extra light through sheer stellar productivity. Some might contain highly active, supermassive black holes, contributing their own enormous luminosity to the total. Some might belong to the growing category of objects Webb was cataloging as genuinely new things that had no clean classification in any prior framework. What the team could not do was make the 300 fit comfortably inside the standard model without extreme assumptions. Even the most conservative explanations required star formation rates or black hole accretion rates at the absolute upper limits of what the physics allows. And any explanation requiring 300 simultaneous occurrences of a rare extreme event was not really an explanation at all. Adding further weight to the puzzle, Webb's 300 objects were discovered in a tiny sample of the early sky. Its deep field observations cover a fraction of a percent of the full sky. If these objects were uniformly distributed across the universe, and preliminary evidence suggested they were, the full early universe could contain many hundreds of thousands of them. The standard model had predicted a relatively quiet early universe, galaxies building slowly, structures assembling gradually, the first billion years as a time of patient accumulation, Webb kept showing the opposite. An early universe that was furiously active, extraordinarily bright, full of objects that had no business being as massive, as luminous, or as developed as they appeared. 300 more voices saying the same thing, and the pile of evidence was only getting larger. The University of Missouri team was careful in how they framed their discovery. They did not claim to have found a new class of object. They did not claim to have disproved the standard model. They described what they observed with precision. 300 objects, unusually bright, unusually compact, appearing in a specific early cosmic epoch, resisting easy categorization under existing frameworks. That careful framing reflected the culture of the field. Astronomers had learned through Webb's first years that dramatic early claims sometimes softened under scrutiny. But the pattern these 300 objects added to was not softening, it was hardening. Every year of Webb data revealed more examples of the same fundamental problem. The early universe was producing too much, too fast, too soon. And the magnitude of the excess, not a few percent, not a factor of 2, but sometimes a factor of 10 or more above model predictions, left less and less room for any adjustment within the existing framework to close the gap. One of the clearest signatures of a mature galaxy is rotation. Look at a spiral galaxy like the Milky Way. Stars orbit the center in a flat disk. Gas flows in predictable circular patterns. The entire structure spins like an enormous, slow pinwheel, hundreds of thousands of light years across. That spin is the accumulated result of billions of years of ordered gravitational collapse, angular momentum building up as gas falls inward, and star formation settling into a rotating disk over time. Rotation is how galaxies grow up. In 2026, Webb released results from a survey of more than 250 early galaxies seen when the universe was between 800 million and 1.5 billion years old. The survey examined their structure and their motion in detail. Scientists expected a mix, some irregular blobs still forming, some early disks beginning to show organized rotation, a picture of galaxies in different stages of growing up. What they found was mostly chaos. The vast majority of these early galaxies were turbulent, asymmetric, gas moving in multiple directions at once, clumping and fragmenting rather than settling into smooth rotating structures. Even the most massive ones in the sample galaxies that had already built up enormous amounts of stellar mass, equivalent to tens of billions of solar masses, showed little or no coherent rotation. Under the standard model, a galaxy that massive at that epoch should have developed at least a primitive disk. Gravity and angular momentum working together over hundreds of millions of years impose order. That is the prediction. Gas settles, orbits circularize, a disk forms. It was supposed to be one of the most reliable features of early massive galaxies. These galaxies had ignored the prescription entirely. One galaxy in particular stood out from the rest, a massive, already quenched galaxy done forming stars, already dead with no spin whatsoever, a static, disordered pile of stellar mass sitting in the ancient universe with no rotational motion, no disk structure, and no clear mechanism that could have removed its angular momentum so thoroughly. The lead scientists described it in language unusual for academic papers. This object, they wrote, arriving at this kind of mass at this point in cosmic history, without any organized rotation, presented a direct challenge to the standard picture of how galaxies assemble. In plainer terms, this galaxy had grown up, burned out, and died before it ever learned to spin. Standard physics had no clean explanation for how that was possible. The early universe kept finding new ways to defy the rulebook, and the defiance was about to go interstellar. But the non-rotating galaxy was not just a curiosity. Angular momentum, the physical property that causes things to spin, is conserved in physics. You cannot create it or destroy it. A galaxy assembling from collapsing gas should naturally spin up, just as a skater spins faster when they pull their arms in. For a galaxy to end up with almost no rotation, something extraordinary must have removed its angular momentum. One possibility was formation through a rapid, violent merger of multiple clumps arriving from different directions at once, with their rotations cancelling each other out. That kind of chaotic assembly was physically possible in the dense early universe. But producing a galaxy this massive, this way, this early, and shutting it down immediately afterward, pushed every parameter in those models to their limits at once. The early universe was solving problems that standard physics had not written solutions for. In March 2026, Webb spotted something it was never specifically designed to look for: the most distant jellyfish galaxy ever observed. Jellyfish galaxies are among the strangest structures in the visible universe. They are galaxies undergoing a process called ram pressure stripping. As a galaxy falls through the hot, diffuse gas that fills the space inside a massive galaxy cluster, that surrounding gas acts like a headwind. It presses against the infalling galaxy from the front, tearing away the cold gas the galaxy uses to form new stars and dragging it behind in long, glowing streamers. New stars ignite inside those streamers as the stripped gas cools and condenses, creating tails of blue newborn stars stretching hundreds of thousands of light years behind the galaxy's main body. They look, with striking accuracy, like jellyfish drifting through water. Before Webb, the most distant confirmed jellyfish galaxy was seen when the universe was roughly 4 to 5 billion years old. Scientists assumed that ram pressure stripping, which requires a dense galaxy cluster filled with hot intergalactic gas to generate the effect, would be rare in the early universe. When clusters had barely begun to form, Webb pushed that timeline back by more than 1 billion years. The jellyfish it found existed when the universe was roughly 3 billion years old. To be there, it needed to be falling through a dense cluster, a gravitationally bound collection of hundreds of galaxies filled with hot gas moving at millions of miles per hour. And that cluster needed to already be massive and developed enough to generate the ram pressure that stripped the jellyfish's gas. That cluster existed. Webb's infrared cameras confirmed it. Dense, massive, active. At an epoch when the standard model said clusters that size should still have been loose, unorganized groups barely beginning to gravitationally collapse. The jellyfish itself showed long tails of newborn blue stars streaming behind it, direct evidence of active stripping. Webb could resolve individual star-forming pockets inside those tails, compact knots of new stars igniting inside gas that had been ripped from the galaxy's body and dragged into surrounding space. This observation was a double anomaly. The jellyfish itself required the cluster. The cluster required an early universe that built large structures faster than any simulation predicted, and both the jellyfish and the cluster required an environment far more violent and far more organized at 3 billion years than the standard model allowed. Every piece of evidence was connecting to every other piece. The early universe was not just producing individual surprising objects. It was building entire systems, galaxies, clusters, filaments, and the relationships between them on a timeline that outran every model scientists had written for it. The jellyfish galaxy discovery carried one more implication that scientists noted carefully. The gas tails streaming behind it, full of newborn blue stars, were forming stars in open intergalactic space, far from any galaxy's main body. Star formation in stripped tails is a process studied extensively in nearby galaxy clusters, where ram pressure stripping is common today. But finding it at 3 billion years after the Big Bang meant that star formation was happening in environments science had assumed were too sparse, too violent, and too early for such a process. Wherever Webb looked in the early universe, processes that were supposed to be rare or impossible were appearing as standard features. The universe's early toolkit was more varied and more powerful than any prior telescope had revealed. By mid-2026, 4 years into Webb's scientific operations, the evidence had reached a threshold that the astronomy community could no longer approach cautiously. Individual anomalies can be explained away. A handful of unusually massive early galaxies might reflect a statistical fluke in Webb's targeted observations. One naked black hole might represent an exotic edge case. An unusual dead galaxy might have a mechanism science had simply not identified yet, but the catalogue of anomalies had stopped looking like a list of exceptions. It had started looking like a pattern. The impossible early galaxies, too massive, too bright, too chemically complex. The dead galaxies quenching too early, with mechanisms that existing models could not reproduce. The naked black holes forming before their galaxies, flipping the textbook sequence of cosmic assembly. The little red dots, hundreds of thousands of compact, bright, crimson objects confined to one specific cosmic era, vanishing entirely afterward, matching no known category. The blue monsters, blazing blue galaxies with almost no dust, defying every prediction for early star-forming systems. The Hubble tension confirmed real at 5 sigma, with no measurement error to blame. The evolving dark energy confirmed at 3 to 4 sigma across multiple instruments. The elongated early galaxies consistent with warm or fuzzy dark matter, inconsistent with cold dark matter. The cosmic dipole anomaly confirmed at 5.4 sigma, pointing toward a universe that is not as uniform as the standard model requires. Every one of these had been independently verified by multiple teams. Every one had survived scrutiny. A review paper circulated in 2026 summarized the situation plainly. There was, the authors wrote, a growing chasm between theory and observation related to the early universe. The chasm was not closing, it was widening with every new observation. And the phrase that the lead researcher on MOME, Z14, had used, that the universe looks nothing like what we predicted, had become a common refrain at conferences and in paper abstracts across the field. Scientists were careful to be precise about what this did and did not mean. It did not mean the Big Bang was wrong. It did not mean the universe was a different age. It did not mean general relativity was broken. The cosmic microwave background still matched its predictions. The abundance of light elements from the first 3 minutes still checked out. The large-scale structure of today's universe still conformed to standard model expectations. What the chasm described was the failure of one specific part of the model, the prescription for how the first structures formed in the first billion years. That prescription, built before Webb existed, had been overtaken by evidence from a telescope that could see further and with greater clarity than anything previously built. The standard model was not dead, but it was incomplete in a way that could no longer be papered over. What made this moment in cosmology unusual was the specific location of the failure. Most scientific theories break at the edges in extreme conditions, at very high energies, at scales beyond their original design. The standard model was failing at the beginning, at the very epoch it was supposed to describe best, because that epoch was anchored in the Big Bang whose echoes the cosmic microwave background preserved so precisely. The model's foundation was holding, but the layer above it describing how the first objects formed had cracked. Webb was the telescope built to test that layer directly, and the test results were in. Before concluding that cosmology was broken, it was worth pausing on what had not broken. Lambda, cold, dark matter, the standard model of cosmology, is still the most successful large-scale theory of the universe that science has ever produced. And that success is not marginal, it is extraordinary. It correctly predicts the detailed temperature fluctuations in the cosmic microwave background, a map of the universe when it was only 380,000 years old, down to 3 decimal places of accuracy. That is roughly as precise as any prediction in all of physical science. It correctly predicts the relative abundances of hydrogen, helium, and lithium produced in the first 3 minutes after the Big Bang, a calculation known as Big Bang nucleosynthesis that has been confirmed by observations of the oldest, most pristine stars in the universe. It correctly predicts the distribution of galaxy clusters across billions of light-years of present-day space. It correctly predicts the existence and large-scale structure of the cosmic web. It correctly describes how the universe's expansion rate has evolved across its full 14 billion-year history, with the one recent caveat that dark energy might be slightly more complicated than originally assumed. These are not minor achievements. They represent 6 decades of predictions holding up against the most precise measurements ever made. What Webb is challenging is a layer built on top of this foundation, a set of assumptions governing the very earliest stages of galaxy and black hole formation. Scientists call it subgrid physics, the rules describing processes that happen at scales too small to simulate directly in full universe models. How efficiently gas collapses into stars in the first billion years. How quickly the earliest black holes accumulate mass. What the first generation of stars looked like. How fast galaxies build up their stellar populations. These rules were built by extrapolating from observations of the modern universe backward in time. Webb is revealing that the extrapolation was wrong. The early universe did not work the way the modern universe does. It was faster, more efficient, more violent, and more complex. In the history of physics, this kind of discovery is not a crisis. It is the moment when a theory reveals its range of validity, the conditions under which it works, and the conditions under which it breaks down. Newton's gravity worked beautifully for everything in the solar system, and then broke down when speeds approached the speed of light. Einstein's relativity extended the range without discarding what Newton got right. Webb is showing where the standard model's subgrid physics breaks down. Whatever comes next will extend the range, not replace the foundation. The foundation holds. The early universe prescription needs to be rewritten. That rewriting would not be simple. The subgrid physics Webb was challenging represented decades of careful calibration against the best available pre-Webb data. Replacing it required understanding the physical mechanisms behind each discrepancy, why early star formation was more efficient, how the first black holes grew so fast, what produced the little red dots and blue monsters. Each of those questions was the subject of active, competitive research. None had been definitively answered, but the fact that they were all being asked simultaneously, driven by the best observational data ever collected, meant the field was moving faster than it ever had before. The next version of the early universe prescription would be built on Webb's data, and it would be more surprising than anything scientists expected to write when Webb launched on Christmas morning of 2021. Webb was not fighting the mystery alone. In June 2025, the Vera C. Rubin Observatory in the mountains of Chile opened its eyes for the first time, and what it was built to do was fundamentally different from anything Webb could accomplish. Where Webb stares at tiny patches of sky in extraordinary depth, resolving individual stars in galaxies billions of light-years away, capturing spectra of objects at the edge of the observable universe. Rubin was built for breadth. Its camera covered an area of sky nearly 50 times wider than the full moon in a single exposure. Every few nights, it photographed the entire visible sky. Everything that moved, changed, brightened, or faded was flagged, catalogued, and archived automatically. In its first year alone, it catalogued over 300 million new astronomical objects. For the purposes of the cosmological crisis Webb had uncovered, Rubin's contribution was structural. It could test whether Webb's deep field anomalies were features of specific targeted patches of sky, or features of the entire early universe. If Webb's impossible galaxies appeared only in certain directions, that would suggest a local sampling issue. If they appeared everywhere, Rubin's wide field data confirmed them. The anomalies were universal. Early results from the first combined analyses of Webb's deep fields and Rubin's all-sky catalogue pointed firmly toward the second answer. The unusual brightness, the unusual mass density, the unusual number counts of early objects all appeared consistently across multiple independent lines of sight. The anomalies were not artifacts of where Webb happened to look. They were features of the early universe itself, present in every direction, at every scale that could be checked. That universality was critical for understanding the scale of the problem. A strange observation that appears in one location can always be dismissed as local. A strange observation that appears everywhere cannot. Rubin was also beginning its primary mission of mapping dark matter across the full sky by tracking how its gravitational influence bent and distorted the light of background galaxies, a technique called weak gravitational lensing. Its dark matter maps would, over its 10-year survey, provide the most complete picture ever assembled of how dark matter is distributed across the universe. Those maps would be a direct test of whether the standard cold dark matter prediction held across cosmic scales, or whether something warmer, fuzzier, or altogether different was responsible for the universe's invisible skeleton. Webb had opened the cracks. Rubin was measuring how wide they ran, and Rubin was already finding things of its own. In its first year of operations, its automated alert system had identified thousands of transient objects, supernovae, variable stars, and objects that brightened and faded on timescales of hours to days that no previous survey had caught in real time. Among them were several candidates for a type of stellar explosion called a pair instability supernova. These are the same explosions that the monster early stars from Chapter 19 were predicted to have produced explosions so energetic that the star leaves nothing behind. In the nearby universe, pair instability supernovae had been theorized but rarely, if ever, confirmed. Rubin's wide-field, frequent cadence survey was catching the candidates that previous telescopes' slower refresh rates had missed. If confirmed, those detections would provide the first direct observational evidence in the modern universe for the kind of stellar death that Webb's chemical fingerprints were suggesting had dominated the early universe. The early universe and the present one, connected through the chemistry of light? In November 2025, a result appeared in Physical Review Letters that deserved more attention than it received outside the scientific community. The question the paper asked sounded simple. How fast is our solar system moving through the universe, and in what direction? The answer, based on standard cosmology, was well established. Scientists had measured our solar system's motion relative to the cosmic microwave background, the ancient heat glow of the Big Bang that fills all of space, and found we were moving at roughly 370 kilometers per second toward the constellation Leo. That speed was accounted for by the gravitational pull of nearby galaxy clusters and the larger scale flow of our local group of galaxies through its cosmic neighborhood. The Boehmer team at Bielefeld University checked this measurement using a completely independent method. Instead of the cosmic microwave background, they used a large catalogue of distant radio galaxies. The idea was that as our solar system moves in a particular direction, galaxies ahead of us should appear slightly more numerous and slightly brighter due to the Doppler effect, and galaxies behind us slightly fewer and dimmer. The size of that asymmetry, called the kinematic dipole, should match the speed predicted by the standard model. Their measurement came back at 3.67 times the expected value, with a confidence level of 5.4 sigma. Two explanations were on the table. Either our solar system was moving far faster than any standard model accounting allowed, pulled by some invisible, enormous mass concentration billions of light years away that the standard model could not produce, or the distribution of galaxies itself was genuinely asymmetric, meaning the universe had a preferred direction, violating the cosmological principle at its most fundamental level. The paper's authors did not mince their analysis. Our current models are being put to the test, they wrote. In either case, something fundamental must change. What made this result particularly striking was that it was not new as a signal. Earlier studies of distant quasars had shown similar anomalies in the same direction. The Boehmer result was the most statistically significant confirmation yet, using a larger and more precise dataset than any previous analysis. The universe was either larger in its asymmetries than the model allowed, or something enormous and invisible was pulling everything in our cosmic neighborhood far faster than it should be moving. Either way, the standard model had a serious problem. The Boehmer team concluded their paper with a direct statement that circulated widely in discussions among cosmologists. The result, they wrote, was inconsistent with the standard cosmological model at high significance, and the inconsistency pointed toward one of two fundamental revisions. Either the large-scale structure of the universe was genuinely asymmetric, or the matter distribution in the universe extended its influence on cosmic motion far beyond what the standard model's homogenization scale allowed. In either case, the assumption of a perfectly smooth, directionless universe at large scales the cosmological principle that every equation in modern cosmology depended on was in trouble. Scientists responding to the paper were careful to note that confirmation from additional independent datasets was needed before the anomaly could be considered proven. But the accumulation of evidence pointing in the same direction earlier quasar studies, the radio galaxy dipole, and related anomalies in galaxy cluster distributions was becoming difficult to dismiss as coincidence. At this point in the story, it was worth asking what scientists actually believed. The press descriptions of Webb's findings had sometimes used dramatic language. Cosmology broken, the Big Bang overturned, the universe older than we thought. These headlines were exciting. They were also misleading. The Big Bang was not overturned. No peer-reviewed paper from the Webb era claimed it was. The evidence for the Big Bang, the cosmic microwave background, the abundance of primordial elements, the observed expansion of the universe, was as solid as any evidence in all of physics. None of it was touched by what Webb found. What Webb found was that the first billion years of the universe's history, the specific period when the first stars ignited, the first galaxies assembled, and the first black holes grew, did not match the simplified models that had been used to describe that epoch. Those simplified models were not fundamental physics. They were approximations, rules of thumb that stood in for processes too complex and too small scale to simulate directly in full universe models. The efficiency with which gas converts into stars, the speed at which black holes accumulate mass, the mass of the first generation of stars. None of these were derived from fundamental principles. They were estimated from observations of the modern universe and applied backward. Webb showed those estimates were wrong. The early universe was more efficient, more violent, more complex. It operated under conditions so extreme: primordial gas purity, radiation environments, dark matter densities, that extrapolating from today's universe was like using the rules of a slow river to predict the behavior of a waterfall. What was being revised was not the story of the Big Bang. It was the chapter on what came next. The chapter on how the first objects formed and grew and died in the universe's first billion years. That chapter was wrong. It needed to be rewritten with better data, and Webb was providing that data at a pace that had never been possible before. The foundation of cosmology was intact. The early chapters were being revised. That distinction mattered, because revising a chapter and tearing down the building were very different things. Scientists who had studied the history of physics drew comparisons to earlier moments of productive crisis. In the 19th century, the discovery that light traveled at a constant speed regardless of the observer's motion shattered the Newtonian concept of absolute space and time. For nearly 2 decades, physicists argued and measured and theorized. The resolution was not the destruction of physics. It was the creation of special relativity, a new framework that included Newtonian mechanics as a limiting case and extended the description of reality to speeds and conditions Newton had never imagined. Similarly, the discovery in 1998 that the universe's expansion was accelerating did not destroy the Big Bang model. It required adding dark energy to the standard model and opening an entirely new field of observational cosmology dedicated to understanding it. Webb's discoveries were pointing toward another extension of that kind, a new version of the early universe story, deeper and more accurate than the old one, that would include the old story as a rough approximation of what actually happened. That is what science does when it works at its best. One of Webb's original scientific goals was to map the reionization epoch, the crucial transition when the first stars and galaxies produced enough ultraviolet light to tear apart the thick neutral hydrogen fog filling the early floating universe and let light travel freely through space for the first time in cosmic history. Before reionization, the universe was opaque. Every photon produced by the first stars slammed into neutral hydrogen atoms and was absorbed, scattered, lost. The universe was a closed room with the lights on, but the walls absorbing everything. Reionization knocked down those walls. It made the universe transparent. It allowed the light of the first galaxies to travel freely across space, eventually reaching Webb's sensors 13 billion years later. Scientists estimated that reionization happened gradually, between roughly 400 million and 1 billion years after the Big Bang. That estimate was based on the best pre-Webb data available. Webb proved the estimate was too conservative. MOME Z14, existing only 280 million years after the Big Bang, was actively clearing its surrounding hydrogen fog, blasting ultraviolet radiation outward and creating a bubble of transparency in the dense neutral hydrogen around it. Reionization was already happening at a scale that mattered before 400 million years had passed. Webb also identified a population of small, intensely star-forming galaxies from roughly 1 billion years after the Big Bang, dubbed little green galaxies, based on the wavelength of their dominant emission that appeared to be among the primary drivers of reionization. Their individual ultraviolet outputs were modest, but they were extraordinarily numerous. Collectively, they poured more ionizing radiation into the surrounding universe than any larger, more famous galaxy class. And in March 2026, Webb confirmed the earliest supernova ever detected a star that exploded when the universe was only 730 million years old. The gamma-ray burst generated by this explosion was caught by telescopes around the world, and Webb's rapid response provided the most detailed observation ever captured of a stellar explosion at that distance, including a spectroscopic fingerprint of the host galaxy, which turned out to be smaller and younger than anyone expected to find hosting a star massive enough to die so explosively. Each data point pushed the reionization timeline earlier. Each one suggested the first stars and galaxies were more productive, more powerful, and more numerous than any model predicted. The universe lit itself up faster than the rulebook allowed, and the consequences of that early illumination rippled through everything Webb was seeing. An early cosmic web exposed to intense radiation earlier than predicted. Early galaxies stripped or enriched by that radiation in ways no model had accounted for. Early black holes seeded by the first stellar deaths before the standard formation timelines had even begun. The supernova observation opened one more specific door. The gamma-ray burst that triggered it illuminated a column of intergalactic gas stretching billions of light-years toward Earth. By analyzing the absorption lines in that illuminated gas, astronomers could measure the chemical composition of the material, filling the space between early galaxies. The result: more oxygen, more carbon, more silicon in the intergalactic medium than the universe should have had time to produce. The early universe had not only lit up faster than predicted, it had chemically matured faster. Stars had formed, burned, and scattered their enriched remnants across intergalactic space on a timeline that outran every model. In every direction and at every scale scientists could measure, the early universe was running ahead of the clock. In May 2026, Webb released its most ambitious structural map yet, the clearest, most detailed three-dimensional picture ever produced of the cosmic web, the enormous filamentary skeleton of dark matter and gas on which every galaxy in the universe is threaded. The map covered a volume of space stretching across billions of light-years. It resolved individual filaments, threads of dark matter, each containing hundreds of billions of solar masses, connecting galaxy clusters like glowing knots on an enormous net. Between those filaments, vast voids stretched hundreds of millions of light-years across, containing almost nothing. The structure was not a surprise. Dark matter simulations from the 1980s and 90s had predicted exactly this kind of filamentary network emerging from the quantum fluctuations of the Big Bang. That prediction had been one of the Standard Model's great successes, confirmed qualitatively by earlier surveys, now confirmed in unprecedented detail by Webb. But the details inside the structure told a more complicated story. The filaments were clumpier in some regions and smoother in others than any simulation of cold dark matter produced. Galaxy clusters at the nodes of the Webb were more massive in some locations and less developed in others than the standard timeline predicted for their cosmic age. And at the highest redshifts, Webb could probe the most ancient corners of the map. The Webb showed signs of organizing itself faster than any cold dark matter simulation had ever generated. The same theme, written in the large-scale structure of space itself. But the map also revealed something genuinely new and beautiful that no prediction had specifically anticipated. Woven between the filaments, in the space connecting early galaxy clusters, Webb's infrared sensors detected faint wisps of glowing gas, thin streams of hydrogen heated by the ultraviolet radiation of nearby galaxies and quasars. These gas filaments were raw cosmic fuel in transit, material slowly flowing along dark matter highways toward the galaxy clusters where it would eventually collapse into new generations of stars. For the first time, astronomers were watching the fuel delivery system of the early universe in real time, raw ingredients traveling to their destinations. The cosmic supply chain of galaxy formation, made visible by a telescope sensitive enough to capture light that had been traveling for more than 12 billion years. The universe was building itself, frame by frame, and every frame looked different from the model's prediction. The cosmic Webb map also posed a specific challenge to the cold, dark matter framework. The standard model predicted a specific relationship between the mass of dark matter halos, the invisible spheres of dark matter surrounding every galaxy, and the masses of the galaxies inside them. In the simulations, more massive halos should host more massive galaxies, with a predictable ratio that held across cosmic time. The new Webb map allowed scientists to test that relationship at higher redshifts than ever before, by comparing the positions and brightnesses of galaxies to the dark matter filaments they sat inside. The relationship held roughly, but the scatter around it, the variation in galaxy mass at any given halo mass, was larger than cold dark matter simulations predicted, especially at the earliest epochs. Galaxies in the early universe were either dramatically overmassive or dramatically undermassive for their dark matter halos, at rates that cold dark matter could not easily reproduce. The map had confirmed the Webb existed. It had also confirmed that the Webb's inhabitants were following rules the model had not anticipated. Of everything Webb found in the early universe, one category appeared again and again across years of observations and resisted every attempted explanation: dormant black holes. Not feeding black holes blazing with light as they consumed gas. Dormant ones, silent. Invisible in every wavelength except through their gravitational influence on surrounding stars or through the faintest infrared whispers of their immediate neighborhoods. Black holes that had grown to enormous size and then simply stopped feeding, sitting in the early universe, like switched-off engines inside galaxies too small to have produced them. In 2025, Webb detected the most distant dormant black hole ever found. It sat inside a galaxy so early and so small that the black hole's estimated mass was larger, by some calculations, than the total mass of all the stars in the galaxy combined. A black hole that outweighed its own galaxy, completely quiet, completely dark, offering no emission line, no X-ray glow, no radio pulse, just gravity. In the standard model, black holes and galaxies grow together through a regulated relationship. Gas flows in, some forms stars, some feeds the central black hole. The black hole's energy output limits further gas inflow, and the system reaches a stable equilibrium. The mass of the black hole ends up proportional to the mass of the galaxy's stellar bulge, a relationship that holds across thousands of galaxies observed today. Finding a black hole that had massively overgrown its galaxy broke that relationship at the most fundamental level. It implied the black hole had assembled first, at extraordinary speed, before the galaxy's stellar population had time to catch up. The standard growth together model had no mechanism for producing a result like that in the first few 100 million years. This was the naked black hole problem from Chapter 10, restated in a different form, and it kept reappearing. Multiple groups using different Webb datasets found similar examples at different epochs in the early universe. Black holes punching above their expected mass class, galaxies lagging far behind their central engines. Scientists propose that in the primordial universe, the conditions for direct gas collapse into massive black hole seeds were far more favorable than they are in today's galaxy-filled, radiation-saturated cosmos. In the pure, cold, undisturbed gas clouds of the very early universe, enormous masses of hydrogen could have collapsed directly into black holes without passing through a stellar phase at all. If true, the seeds of every supermassive black hole in existence today, including the one at the center of the Milky Way, 4 million times the mass of our Sun, may have formed before the first stars in those galaxies ever ignited. Black holes first, galaxies following. The universe building its foundations before its walls. The dormant black hole mystery fed directly into the broader question of what the first objects in the universe actually were. If black holes formed first before galaxies, before significant numbers of stars, then the Standard Model's sequential assembly was simply backwards for the early universe. Gas formed stars, stars formed black holes merged into supermassive ones, galaxies assembled around them. That was the standard sequence. Webb's dormant black holes, naked black holes, and overmassive black holes all pointed to a different order. Enormous black holes appearing fully formed, surrounded by too few stars to explain their growth. In a universe too young for standard mechanisms to have operated, scientists had proposed for years that direct collapse gas falling straight into a black hole without forming stars might explain some early cases. Webb was accumulating the sample needed to test whether direct collapse was rare or dominant. Each dormant black hole added one more data point. By the summer of 2026, it was possible to count the confirmed anomalies between Webb's observations and the Standard Model, peer-reviewed, independently verified, statistically significant. Galaxies too massive to exist in the first billion years of cosmic history, confirmed across multiple surveys by multiple teams using multiple instruments. The most massive examples exceeded the Standard Model's upper limits by factors that no plausible adjustment could easily close. Dead galaxies quenching too early, confirmed, with a record holder shutting down at 700 million years after the Big Bang, in an epoch where the Standard Model predicted only rapid growth. A naked supermassive black hole existing before its host galaxy, confirmed, and subsequently found to be one example of a broader population of early black holes that preceded the galaxies around them. Hundreds of thousands of little red dots with no clear category, appearing and then vanishing from a specific cosmic window, confirmed as real, confirmed as unlike any known object class, with multiple competing explanations and no consensus. Blue monster galaxies with near zero dust that no Standard Model reproduces, confirmed in multiple independent datasets. The Hubble tension, confirmed real, confirmed not a measurement error, holding at 5 sigma with Webb's precise Cepheid measurements. Evolving dark energy from the DESI surveys, confirmed at 3 to 4 sigma across 2 independent data releases. Elongated early galaxies, inconsistent with cold dark matter predictions, confirmed in surveys of hundreds of early galaxies. A cosmic dipole anomaly more than 3 times larger than the Standard Model allows, confirmed at 5.4 sigma across independent radio galaxy catalogues, the earliest supernova ever detected at 730 million years after the Big Bang, reshaping the reionization timeline, confirmed by Webb's direct spectroscopic follow-up. Early galaxy clusters too massive and too dense for their epoch, confirmed through multiple jellyfish galaxy detections and direct cluster observations. Each line on that list came from different researchers, working with different data, applying independent methods. No single team produced all of it. No single telescope observed all of it. It emerged collectively, convergently, from the entire field of observational cosmology working in parallel, and the list was still growing. Webb was still running, Rubin was still scanning, the square-kilometer array was still being built. Every new observation had the potential to add another confirmed anomaly, close an existing one, or reveal something so unexpected that even the list of anomalies needed revision. The standard model was wounded in the specific place where it described the very beginning of everything. What came next would determine whether that wound could be healed with refinements, or whether something deeper had to change. The scientists who had built careers on the standard model were not despairing. Several of the most prominent voices in observational cosmology had noted publicly that this moment felt different from previous periods of anomalies in the field, and they meant that in a positive way. Previous anomalies had arrived one at a time, been studied in isolation, and often resolved individually. What Webb was producing was a coherent, interlocking picture of anomalies that all pointed in the same direction. The early universe was more active, more efficient, and more structured than the standard model predicted. That coherence suggested the anomalies were not noise, they were signal. And signals that point consistently in the same direction usually mean there is something real at their source. Finding that thing, whatever revision or extension of the standard model explained all the anomalies simultaneously, was the most important open question in cosmology in the summer of 2026. And the telescope responsible for asking it was still pointing at the sky. The answer is out there, and the tools to find it are being built. Webb itself still has years of operational life ahead. Its launch trajectory used less fuel than planned, extending its maneuvering reserves well beyond the original 10-year design lifetime. Every additional year of observation is more galaxies, more spectra, more chemical fingerprints, more chances to catch an early dark star, a new class of impossible object, or a discovery so unexpected it makes everything else look like preparation. On the ground, the Vera C. Rubin Observatory was releasing its first year of data in 2026. Its legacy survey of space and time will, over its 10-year run, catalogue tens of billions of astronomical objects, stars, galaxies, transients, and things with no current name. Its statistical power will allow cosmologists to test the cosmological principle across the full sky at a precision no previous survey has approached. If the cosmic dipole anomaly is a genuine feature of the universe, Rubin will confirm it definitively. If it disappears in a larger sample, that resolution will be equally important. The Square Kilometre Array, a massive radio telescope network under construction across South Africa and Australia, will come online later this decade. With sensitivity far beyond any existing radio facility, it will map radio galaxies across the full observable universe and measure the kinematic dipole with enough precision to determine whether the anomaly reflects genuine cosmic asymmetry or some other cause entirely. If there is an answer to the lopsided universe problem, the Square Kilometre Array will likely find it. The Nancy Grace Roman Space Telescope, when launched, will survey areas of sky hundreds of times larger than Webb covers in a single pointing, capturing enormous statistical samples of early galaxies and testing whether Webb's deep field discoveries hold across the full cosmos. And on the theoretical side, a generation of astrophysicists was rebuilding their simulations from scratch, incorporating dark star scenarios, warm and fuzzy dark matter, revised star formation physics, direct collapse black hole seeding, dynamic dark energy, and the full catalogue of Webb anomalies. Running those simulations against the observations, eliminating what does not fit, refining what does, building, piece by piece, the next version of the story of the universe. Science does not break and rebuild overnight. It inches forward, it tests, it checks, it argues, it takes the most uncomfortable observation and refuses to look away until it has an explanation that holds. Webb forced an entire field to stop looking away. The universe, at the edge of everything, does not match the picture we built for it. It is brighter, more violent, more chemically complex, more asymmetric, and more alive in its first billion years than 60 years of extraordinary science predicted it would be. That is not a failure. It is an invitation. Every major revolution in physics began exactly here. An observation that refused to fit. A gap that would not close. A universe that kept insisting it knew something the scientists did not. When Newton's laws failed for Mercury's orbit, Einstein did not scrap physics. He expanded it. When the universe turned out to be accelerating, cosmologists did not abandon the Big Bang. They added dark energy and built a better model. The pattern is always the same. An anomaly appears, scientists argue about it, instruments improve, the anomaly holds up, a new framework emerges, the old one becomes a special case of the new. That process is happening right now, at the frontier of human knowledge, driven by a gold and silver telescope 1 million miles from Earth, pointing itself at the edge of everything. We are standing at that gap right now, and everything that comes next gets to be a discovery.